In this video, we're going to expand on Newton's second law and talk about the different types of forces that you might encounter. We're also going to introduce the math for some of those forces, which on the Regents reference tables are pretty well organized, and on the AP reference tables a little less so for reasons I don't fully understand. And either way, you're going to notice a couple of other equations kicking around there that also have force in them, which we're not going to worry about yet. Okay? So let's talk forces. The types of forces that you're most familiar with are called contact forces. Contact forces are really any kind of push or pull. Tension in a rope, if you shove somebody, an impact from a collision, any of these types of things are contact forces. The other type of forces are field forces. These are forces that are caused by the changed space around objects. So there are four of those. They are gravity, which we're going to deal with to some degree here, electromagnetism, which we'll talk about in the spring, and these strong and weak nuclear forces, which we're going to deal with a little bit when we talk modern physics at the very end of the year. It turns out that all contact forces are actually electromagnetism, but that's definitely a topic for particle physics in May or June. So first things first, let's talk gravity. The equations look a little bit different on the two reference tables, but they say the same thing. And very commonly, instead of Fg, we're just going to use W for weight, because the force due to gravity is an object's weight. And weight equals mass times the acceleration due to gravity. Or the acceleration due to gravity is equal to the force of gravity divided by mass. So this equation means the same thing. And weight equals mg is the same thing as F equals ma, right? Because weight is a force. So that's the simplest form of gravity, and it only works near the surface of the Earth. Once you move away from the Earth out in space, or you're on the moon or Jupiter or something like that, g is no longer 9.81 meters per second squared. And so, in fact, as you travel up away from Earth, g gets lower and lower and lower and lower, and figuring things out can get pretty complicated and require calculus. So, in any case, that equation is very useful near the surface of the Earth. But once you move away from the surface of the Earth, or you're not talking about the gravity between the Earth and some other object, you can't use that anymore. To that end, studying the planets, Newton discovered a new law of gravity, and this is the law that he really had to invent calculus in order to figure out, and it's called Newton's law of universal gravitation. It's Fg equals g, m1, m2 over r squared. The m's are the masses of the two objects, r is the distance between the centers of those two objects, and g is this thing called the universal gravitational constant, which Newton figured out in some clever ways, approximately, which we're not going to worry about. You can find it on your reference tables for Regents and for AP right on the front. What this equation says is that gravity acts between any two objects and every two objects that have mass. So anything that has mass has a gravitational field. This field extends out into space and influences the things nearby. And that's pretty neat. This is why it's called universal gravitation. However, look at the value of g again. 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. That number is super tiny, and what it tells us is that gravity is really weak. You don't see big fat guys like me walking down the hallway and having 7th graders sucked out of line and start to orbit around them. Gravity doesn't have that kind of effect, right? Okay? Because I'm just not nearly big enough. When I'm sitting in front of the class and you're sitting in class, is there gravitational attraction between the two of us? There is, and you can calculate it. And when you do that, you're going to find that it's a very, very small number, because this gravitational coefficient, the universal gravitational constant, which I often call just capital G or big G, that is a really, really tiny number representing just how weak gravity is. This 1 over r squared behavior of gravity is what we call an inverse square law. What it tells us is that when you get twice as far away, gravity isn't twice as weak. Gravity is 4 times as weak. At 3 times further away, it's 9 times weaker. At 4 times farther away, it's 16 times weaker, and so forth. This is an inverse square law. Gravity is not the only law that follows this, and so that type of behavior got its own name. And a final note about gravity. In 1905, several centuries after Newton, Albert Einstein determined that gravity is significantly stranger than Newton ever imagined. So we had an idea about how the universe worked. Newton refined that idea and created something better and improved our understanding. And then Einstein came along and did something even better that improved our understanding further. This is how science works. Now, is Einstein's understanding perfect? Do we fully understand how gravity works now? After over a century since Einstein came up with his theory of general relativity, the answer to that question is, we're not sure. It might be the whole story, but we suspect it's not. Either way, we haven't had any experiments as of yet that has proven him wrong. So we'll see. Our next force that we're going to talk about is friction. Friction happens between any two objects that are in contact. So when they slide against each other, that creates friction. Friction both opposes motion and creates heat, which you can prove by doing this. You'll feel it, right? Okay, so friction happens whether the two objects are moving or not. If you have two objects that are in contact with each other and you can push and have it not actually really move, this is called static friction. Or you can have one thing sliding across another. This is known as kinetic friction. They're similar, but they're not exactly the same. Even with smooth objects, if you were to zoom way in on them with a microscope, you will find that they are actually quite rough. And when you slide two rough things across each other, all of the nooks and crannies and jagged peaks and things catch and drag as they move. And this is what causes friction. How much they're going to catch and drag is determined by a number that we call the coefficient of friction. This number is different for every two surfaces that are in contact. So there's like infinity factorial different coefficients of friction. Worse, the coefficient of static friction and the coefficient of kinetic friction are usually pretty much always different, with static friction being stronger than kinetic friction. Regents class, you have a chart on your reference tables that shows some common coefficients of friction. And for the AP class, it's on page 101 of your book. In neither case will you have to memorize these. Regents, you can always look them up on your reference tables. AP, if you need a coefficient of friction for a problem, either you're going to have to calculate it or it will be given to you in the problem. So here's the equation for friction. It's force of friction equals the coefficient of friction times what we call the normal force. Let's break those down. The coefficient of friction, represented by the Greek letter mu, that coefficient, that's what you can look up. And the normal force, normal in this case is a mathematical word that means perpendicular. If you have an object that's sitting on a surface, the force that that surface is pushing on the object is perpendicular to the surface. If you tilt the surface, the force is still perpendicular. So normal just means perpendicular. The chair is pushing up on me because my force on it is down. They're opposing each other. So normal force is a contact force. And the way to interpret the coefficient of friction is as the percentage of the contact force which contributes to a frictional force. For most normal surfaces, the coefficient of friction maxes out at 1. It is possible with soft rubber and grippy Velcro and things for it to go above 1, but those are extraordinary circumstances that really only happened once we developed the technology to create some special materials. On a flat, horizontal surface, the normal force of an object is always equal to its weight. Think about that. If you've got a thing with an object sitting on top of it, gravity is pulling it downward with a force equal to, well, mg on Earth, right? And it's not moving, so there has to be an upward force, mg, preventing it from moving. On an angled surface, gravity isn't pulling down the ramp, gravity's pulling straight down. And so what's preventing it from moving? It's a combination of gravity and friction. So on a flat horizontal surface, normal force is equal to weight. In any other circumstance, we're going to have to do something else to figure that out, and that'll come later. So if you were paying close attention, you saw that there's a difference in the equations on the two reference tables. The Regents reference tables say force of friction equals mu times normal force, coefficient of friction times normal force. Whereas the AP reference tables doesn't have an equal sign, it has a less than or equal to sign. Both classes have to understand the significance of that, even though for some reason the Regents reference tables uses an equal sign. So here's the deal. Static friction and kinetic friction are a little different. If the two things are sliding, that less than or equal to is equal to. The amount of static friction between two objects depends on the normal force and the coefficient, and that's it. But think about moving a piece of heavy furniture, okay? If you push on it, if you're not pushing on it, the force on it is 0, and the frictional force opposing you is also 0. If you push on it a little bit, but not hard enough to move it, the frictional force pushing back has to equal the force you're pushing with. If it didn't, then the couch would be moving. It would have a net force. You push a little harder, the frictional force increases. You push even harder, the frictional force increases even further. And so the frictional force, the static frictional force, can adjust itself from 0 up to a maximum value. Once you exceed that maximum value, the friction isn't strong enough anymore, the whole thing starts to move. You'll feel the furniture jerk, and then because static friction is almost always stronger than kinetic friction, you'll have to back off to keep it moving at a constant speed. If you kept pushing as hard as you were to get it moving, you'd accelerate it the whole way. So that less than or equal to sign is important. It tells us that static friction in particular is adjustable. It goes from 0 up to that maximum value. Kinetic friction, however, stays at just that one value, assuming the coefficient of friction and normal force remain constant. Air resistance, by the way, is a type of frictional force. It's the friction between you and the gases surrounding you or your car and the gases surrounding your car. We're going to talk about that generally, but we are not going to do any math on it. It's significantly more complicated and depends on your shape, your aerodynamics, and your speed. It's a very interesting topic. It's just outside the bounds of this course. The final two contact forces don't have their own equations, but you should know them. Anytime we're talking about the force in a string or rope or piece of chain or something like that, we're going to call that tension. And anytime you have a force when one object hits another, that's an impact. Whatever those happen to be, we'll just give you a number or make you find a number. It's not going to involve its own equation. So those are your major types of forces and some of the equations you're going to have to use to solve problems with them. In our next video, we're going to talk about something called a free body diagram, which is a tool that we use to make solving problems with forces significantly easier to visualize and solve.